Hello, I'm here today to share with you some lessons and observations from SafetyCulture's migration from a managed PostgreSQL service to our own self-hosted PostgreSQL Citus clusters. What is SafetyCulture and what do we do? We build an operations platform for businesses in basically any sector or industry. The product is very customizable. Check out our website, safetyculture.com, if you want to learn more. We're always on the lookout for great engineers with PostgreSQL experience. So to give you some quick background on why we ended up using Citus, an open source extension for PostgreSQL, we need to talk about understanding some of the challenges you can have in scaling Postgres for certain workloads. SafetyCulture began as a humble mobile application with no data syncing capabilities. Over time, the product has evolved from that initial basic tool to a full product suite, including data syncing and reporting capabilities for mobile devices, web browsers, API access for third-party integrations, etc. We now also support IoT sensors and other growing product capabilities. Our growth has been rapid and challenging at times on our infrastructure and people, with the typical startup scaling constraints around engineering priorities and the usual challenges of where it is best to prioritize engineering effort. This led us to make some decisions in our past when we had a smaller team that was sometimes a compromise to address the short-term problems, but also trying to lay a good foundation for the future. A few years ago, we moved our primary data stores away from NoSQL storage technology to PostgreSQL. At the time, iterating and tuning our data models moderately while also rapidly expanding out our product capabilities. The next iteration of our data store journey was working towards addressing our managed PostgreSQL limitations we could see approaching in the not too distant future. Those limits were individual table size. Our largest table at the time of migration to our self-hosted Citus cluster was greater than 12 terabytes, with many thousands of transactions per second, mostly an update-heavy workload that is built around a single JSONB column. This is not a great data model pattern. It's not recommended you do something similar if you can avoid it. The amount of write-ahead log generation with such a setup can be challenging when trying to meet recovery time targets, in addition to the wasted I/O on the server due to the way JSONB updates rewrite the entire value. Given the size of our largest table, the growth rate and the competition for engineering time versus refactoring existing data models, and the growing challenges in making the existing data model scale, we opted to tackle the infrastructure side of the problem first. This way, we knew that if we didn't complete any other work in a timely manner, we'd at least alleviate the known infrastructure limitations without making any major changes. This is where the business case for Citus shone through over other solutions, as it allowed us to be flexible in the approach and ordering of what work was done first. Deploying and managed a self-hosted database can be challenging at times. You have no vendor to really rely on for specific tuning or fixes. You can engage third-party contracted support if you need it, though. There are various companies who do a great job at this. The open source community, though, is excellent with PostgreSQL. It's very welcoming and very technically competent. Organizations all have their own nuances around how they operate. Some are happy to accept and work with rapid changes, while others may require various design or architecture reviews before proceeding with large changes. In my experience, it was difficult to get other engineers and leaders completely on board with the work required before we all had a reasonably equal understanding of where the limits in the existing systems were, how fast we were approaching them, and what our possible options were to address those limits. A healthy discussion on alternative solutions available and the various trade-offs we'd be making implicitly and explicitly with those choices also helped to contribute to the overall commitment of work towards moving our existing PostgreSQL workloads over to Citus and sharding them. Before embarking on a project to deploy Citus, I'd recommend people undertake a non-biased self-assessment of where they are with their PostgreSQL usage. Self-hosting and managing all of the system yourself isn't a minor amount of work. There are new complexities involved given the distributed nature of the system. There are many moving parts that can go wrong or have subtle failure cases. I'll touch on some of those later. You should consider, is taking on the complexity of a self-hosted solution going to bring in additional benefits that outweigh the increased complexity and responsibilities? Does the team have a shared understanding of why they need or want to use Citus? Making a decision to implement a technology because you want to use it doesn't mean it will be a good fit and can ultimately create more work for you over the long term. If Azure is an option for you, then you may be able to get the best of both worlds easily enough. Be wary of prematurely optimizing or overbuilding your infrastructure. You can always migrate your data later using tools such as PG Logical or foreign data wrappers in a self-controlled environment. Once you have the data volume that begins to justify sharding, it makes sense to move to a sharding data model. Have you undertaken tuning work on your current database setup? Are you leaving performance optimizations unrealized? If you are, it's probably worth looking at that first. Can you just increase the size of your current database virtual hardware on a managed platform? You can grow a long way on a large virtual machine these days. Are you measuring the rate of resource usage growth so you can back up any statements about needing to implement sharding with actual data? Are you memory, disk IO, or CPU bound for your workload, or a combination of all of those? Can you distribute your data using PostgreSQL native partitioning and foreign data wrappers? We did consider this, but didn't want the transaction limitations presented by this sort of setup. But it was something we looked into first. It was attractive to stick with the managed PostgreSQL vendor with and a solution would allow foreign data wrappers and remote shards or remote partitions. For us, though, a major consideration was, can we support the growing product usage and customer data growth while also increasing the compute and parallelization of the workload over more database servers with proper transaction support? With Citus, it was a solid yes, and we had accumulated enough data and analysis to show where the growing trends were projected to hit resource usage limits on a single server solution. Introducing change in a small organization is easy. You can just have a few conversations and typically be done with things and move forward. But if your company is beyond a few hundred people, you may want to consider how you communicate changes internally to keep interest high and hopefully have a few engineers wanting to be part of the database technology change as you deploy Citus. For us, we were able to get a small group of engineers together to work on the proof of concept work and validate a lot of ideas and changes before we rolled out Citus to many different product teams. Once the team had the high-level proof of concept work validated, we now needed to narrow down our possible implementation details for PostgreSQL and Citus infrastructure in our production environment. It was time to investigate the multitude of options available in how you can deploy, build, and manage PostgreSQL with Citus. We reviewed many different tooling configurations, but were able to select choices based on our prior experience as well as relative popularity of various tools based on our own research and experimentation. We wanted to use tools with an active open source community. We reviewed PG Backrest and WLG for backup tooling. We were happy with our testing and validation of PG Backrest and settled on that. Broadly, we found this tool to be quite well tested and widely used within the PostgreSQL community. For monitoring, we already used Prometheus extensively, as well as PG Analyze. So we had this covered quickly with the addition of custom SQL queries used for monitoring by our Prometheus agents. A lot of our monitoring configuration is inspired by PG Watch from Cybertech. Our choice of HA tooling was fairly considered and an area we spent a fair bit of time functionally testing failover operations with. We initially looked into PG Auto Failover, but ran into some bugs and struggled to make it work. It was pretty new at the time when we did start that research. Our fallback options were Patroni and Stolen. Having used Rep Manager before, I didn't really consider it a good fit for our cloud deployment model. Ultimately, we made the choice to use Patroni, given it has the features we needed and desired, a reasonable API, most critically an active community around the tool, which we were able to engage with. Stolen could have been a viable choice as well, but we were happy with Patroni after our initial testing. Functional examples of Patroni configuration helped us R&D how we would set up the cluster reasonably quickly, making our choices on how we would set up Patroni in production fairly clear as well. Our distributed configuration store of choice for Patroni was Console. We'd already been operating Console for a number of years at this point, so we were happy to reuse Console in such a critical system. For replication, initially we started working with asynchronous replication. However, we undertook a number of failover performance testing experiments under simulated load and ultimately selected to use synchronous replication with remote write to memory, as this only had a marginal impact on performance and much better data safety guarantees. Our initial setup was put together quickly by hand with very limited automation so we could get a small cohort of engineers whose main focus is back-end application development using Citus. This was done in our staging environment where we had some bulk sanitized product data to test out various data model changes. It was also critical for us to test query performance, data ingestion, and migration from the existing database systems. This gave us time in the infrastructure management side to consider how we would build, manage, and maintain the infrastructure over a long period of time. Considering our infrastructure is hosted in the cloud, we didn't want to be building a system that would require a lot of care and feeding. We're big believers in cattle over pets infrastructure mentality. We've seen cloud infrastructure fail just like regular servers do. Ultimately, it is just someone else's computer in the cloud, abstracted behind some APIs. To that end, we wanted our system to be managed using tooling as much as possible and eliminate manual provisioning and management operations. The infrastructure had to be self-healing, so we wanted to utilize auto-scaling groups and constructs and other constructs to replace broken virtual machines automatically, rather than paging someone who is on call when the system could recover from minor hardware or software faults without operator intervention. To ensure a repeatable process with our tooling, we started by constructing AMIs using tooling that results in a consistent quality of output. We have a multi-layered process where we construct machine images with defined versions of software and a basic level of configuration. To do this, we used HashiCorp Packer combined with Ansible to install and configure things such as specific software versions that are statically configured for the environment. At this stage, we define what PostgreSQL version and extensions are installed on the host OS. Our monitoring agents, log collection agents, and backup tools such as PG Backrest are also installed at this stage. The source AMI used at this step already has some environment-specific configuration applied by other internal teams, such as our security team. The Packer process bakes into the AMI another set of Ansible playbooks that are run only on first boot of the AMI. We use systemd for this purpose and depend on other network services starting up to trigger that playbook execution. With this playbook, there is tooling to dynamically configure our configuration for the virtual machine based on inputs such as instance tag, instance type, instant disk types, and sizes to configure Patroni and PostgreSQL. Citus at this point is not yet configured with workers, and there is no database provisioning or role creation done just yet. Things like our logging and monitoring agents are configured to point to environment-specific targets at this stage. In this playbook, we've also applied tuning parameters that are needed, such as huge pages configuration and other shared memory allocation, disk provisioning setup, such as file system creation and mounting, which in our case can either be EBS volumes or instance local NVMe storage. Basic Postgres tuning parameters are also, that are influenced by the virtual machine hardware specifications, are tuned like workmem, max connection counts, effective cache size, and other similar settings. We also apply kernel tuning parameters that are influenced by what type of virtual hardware is present. Our AMIs are deployed into an auto-scaling group. We deploy the instances of PostgreSQL in highly available pairs of instances spread across different availability zones to ensure a level of redundancy. Our PostgreSQL instances are accessed via an AWS NLB, which only routes traffic to the primary PostgreSQL server of any HA pair. These NLBs are configured to determine which host is the primary host by using the Patroni API that runs on each instance, which is configured as part of the AWS NLB health check. Our tooling manages the AWS resources using Terraform, which I assume most people are familiar with. To manage the Citus worker node enrollment and the Citus extension, we use another Ansible playbook again. This playbook is set up to run in a job in our continuous integration system, so we're not reliant on a single engineer to run the playbook after infrastructure changes, say from their own laptop. This gives us a centralized place to see who's applied what changes and when, and gives us that level of auditability. This Ansible playbook is configured to target the coordinator node of a specific Citus cluster based on tags defined on the AWS resources. No individual specific host is targeted by an IP address or host name here. The only time we use host names is when we use the NLB addresses for the Citus add node function calls, which are dynamically populated based on the results of the AWS metadata API lookups filtered by specific tags. The same Ansible playbook will also provision databases, extensions, and roles. For secrets, we're storing those in AWS Secrets Manager, and Ansible can dynamically source those for setting up passwords on those roles. These passwords are managed through other tooling, and those secrets are populated through that other tooling as well. And this is overseen by our security team. Terraform is used for part of this infrastructure as well. The Ansible playbook that we run that does the provisioning is configured to be idempotent, so we can rerun it as needed without fear of breaking existing configuration of provisioned resources. We spent a fair bit of time here required to ensure that idempotency, and if someone was following this pattern, strongly recommended you do the same. Our failovers between PostgreSQL primary and standbys rely on the Patroni Health Check API, which the AWS NLB polls. Currently, we only use the primary PostgreSQL server. This is something we may consider changing in the future and update Citus metadata through automation in, say, the Patroni callback scripts on role changes. It would be nice to have a cluster set up that allows us to use the standby servers for read-only workloads as well. Given we have the host deployed inside an auto-scaling group in each availability zone, we're able to have the system replace instances if they are destroyed or terminated. Patroni takes care of initializing instances as they are spun up by that auto-scaling group's policies. And the Ansible playbook that runs on first boot applies the correct configuration based on the system tags pushed down by that auto-scaling group. When we have a new AMI to be deployed to patch software versions or apply other configuration tuning changes, then we have tooling that will destroy the standby instance after the ASG policies updates. We let the ASG launch replacement instances in and let the in-instance Ansible playbook configure the instance appropriately and leave Patroni to initialize the new instance to the standby role and let it resync all the data. This is a hands-off process for us. After that is complete, we can initiate a Patroni switchover to change the standby and primary node roles. Then we can terminate the standby instance again and let the combination of our tooling automatically replace the instances. Overall, we have tooling in place that can completely replace a cluster's underlying virtual hardware and update the AMIs for us just by clicking one button in our CI infrastructure. PostgreSQL or Citus major version upgrades still require some manual work to complete. These will be automated in the future, something that we haven't had to do that frequently yet. To give you a better picture of the big picture overview, each Citus node cluster is made up of 2 PostgreSQL servers with the Citus extension loaded, each in different AZs, contained within their own auto-scaling group with their own NLB for traffic access. This lets us scale out the Citus PostgreSQL worker node HA clusters easily through our tooling by just repeating the same pattern of infrastructure deployment per Citus worker node we want. Our setup was configured and built before Patroni 3 was released, which included Citus support. We're using multiple databases per Citus cluster, which Patroni 3's current Citus support does not support. So we do have a lot of Patroni clusters per worker node cluster or coordinator cluster that we need to manage. Overall, at the moment, our tooling handles this just fine, although we are looking forward to adopt the native support for Citus within Patroni in the future. It did take a bit more explanation in our onboarding documentation and training for engineers to understand the various clusters we have defined at each layer of the system view. As far as I know, Citus wasn't designed to support multiple databases per cluster, so we may run into issues with our deployment. The recommended approach currently is to at least use schemas within one database. This is something we will look to in the future, but I think this is an area Citus is evolving. We ended up spending a fair bit of time trying to work out why we were seeing dropped network traffic, which we originally thought was due to our network load balancers. But after further research and numerous support tickets to our vendor, we identified that we had not applied relevant kernel tuning recommendations that our vendor publish over in GitHub regarding their custom network adapters under high traffic throughput workloads. We have also run into bugs in Citus after adopting various releases within hours of publishing by the Citus team. Now that we are properly running our workload in production, we are definitely more cautious about the release cadence to our larger customer-facing clusters. We do have internal validation and staging clusters that we graduate Citus changes through, and we make sure all our tooling works there as well. A recent release of Petroni introduced some changes in language used on the API. This meant we had to apply a number of changes to our scripts that manage the automated release of AMIs into our clusters. This overall wasn't that much work, but it was important to really read the release notes of the software we are using. In some cases, you may want to pin the versions of software just to ensure stability of your tooling. Testing and validating the clusters with how they perform was critical for our team to really understand how to operate the infrastructure. The few people who initially did the proof of concept work had really no problems, that they'd been immersed in this environment for a while. But as it was time to bring in others into the on-call rosters and polish the runbooks for various engineers to follow during an incident, due to the nature of the testing and validation stage of the work, meant we could break things and really validate how the documentation in those runbooks covered what was going on and what signals to use in our monitoring. We did use this stage to find all the deficient areas of those runbooks. Testing with simulated data will only get you so far. We tested with our real data models and sanitized production data. In some cases, we did have to make changes to our schema. We had issues with foreign key relationships between sharded tables. We also had to adjust a few joins to optimize the queries to not result in large data aggregations back on the coordinator. We potentially could have shipped those inefficient queries to production had we not been diligent in testing. It is worth noting that some queries can be slower if they perform really well on a single system. Keep in mind, you now have the extra network latencies of the sharded tables over multiple systems to take into account. For us, that trade-off of some queries becoming slightly slower was definitely worth it. Overall, the customer experience is much better now. Going live with the existing application workloads in Citus is an interesting topic. There isn't a one-size-fits-all approach that I can recommend to migrate the data. There are nuances and challenges based on various requirements, like can you tolerate downtime, how much or none at all? How large is the data set? It can also present challenges. For our larger databases, we had to rely on foreign data wrappers to insert data into sharded tables. We set up triggers on the source system to capture any changes made there and ensure they were written to Citus over the foreign data wrapper. On the source system, we were able to run a series of select for insert statements to move the bulk of the data into those sharded tables. We couldn't use logical replication here due to the update volume and limited disk space to handle the ballooning WAL on the source system. And logical replication isn't usable with Citus to a sharded table either. Our coordinator had insufficient disk space to accommodate all of the data anyway, so we had basically just pointed us towards that foreign data wrapper method. Foreign data wrappers let us minimize the additional disk usage on the old system as well, as it wasn't affected by WAL activity either. For some of our smaller databases, we were able to use PG logical replication between the old system and the Citus coordinator. With all data fitting on the coordinator, that was fine for us to take that approach, and we can shard some tables later there as they grow. I'd like to say thanks to the Citus team. We've had great support over Slack when we have run into bugs. We did have seg faults for a couple of hours. That was scary just before we went live, but the team had a patch released very quickly. It was amazing to work with such a wonderful team who was able to provide good support over Slack. If you want to contact me about any of the details of our infrastructure or further info on how we made all this work, I'm very active in the Citus Slack channel and happy to take your questions there. Thanks a lot.